Equilibrium constant KEQ is equal to the products to some power x divided by the reactants to some power y, in which we get the exponents from the coefficients of the balance equation. So what does KEQ mean? When KEQ is very large or greater than 1, it is product favor. When KEQ is less than 1, it is reactant favor. Since the equation is products over reactants, and the products are the numerator, the larger the numerator, KEQ is going to be larger. The larger the denominator, the reactants, it's going to be smaller because it's inversely related. There are two types of equilibrium, homogeneous and heterogeneous. In the previous unit, we learned that homo means same throughout, hetero means different. So when we have a homogeneous equilibrium, the reactants and products are in the same state. They could be all solids, they could be all liquids, they could be all aqueous or all gases. If it's a heterogeneous equilibrium, reactants and products are in different states. So you'll have different states of matter. You could have solid, liquid, gas, and aqueous at the same time. Below, there are two reactions that are both decomposition. The water starts at gas and it becomes hydrogen gas and oxygen gas. The hydrobromic acid starts aqueous and breaks into H2 gas and Br2 liquid. When reactions happen, they are not always at equilibrium immediately. So ice tables are tools to help solve reactions reaching equilibrium. I stands for initial, C stands for change, E stands for equilibrium. So whenever the reaction is not at equilibrium or initial concentrations are provided, you must write an ice table. Depending on the math, sometimes you must use the quadratic equation. General format for a quadratic is ax squared plus bx plus c equals to 0. So x is equal to negative b plus or minus square root of b squared minus 4ac over 2a. So let's look at this first problem. In a closed system initially containing 1 times 10 to the negative third molar hydrogen and 2 times 10 to the negative third molar chlorine, and allowed to reach equilibrium at 448 degrees Celsius. Analysis of the equilibrium mixture shows that concentration of HCl is 1.87 times 10 to the negative third molar. Calculate the equilibrium constant for the synthesis of hydrochloric acid from its element. So we know we have to write an ice table. Clue words are initially, containing, and allow to reach equilibrium. So we're going to start this problem by writing a balance equation. It told you it's a synthesis equation from the element. So it's going to be H2 plus Cl2 yields HCl. Next we need to balance, so it's 2HCl. So the ice is going to be ICE, and we're going to fill the table up. My initial concentration for H2 is given as 0.00 times 10 to the negative third molar. For chlorine, it is 2.00 times 10 to the negative third molar. Are initially starting the reaction. There is no product, so HCl is 0. The change is how much the reactants will decrease during the reaction and how much the products will increase during the reaction. To write our change, we must look at our coefficient of the balance reaction, because for every 1 hydrogen and every 1 chlorine, 2 hydrochloric acids are produced. The change is, if we say H2 will change by a X amount, chlorine will also change by an X amount because it's a 1-to-1 ratio. However, the hydrochloric acid will change by 2 times that X because it is twice, because it's a 1-to-1-to-2 ratio. So for every 1 H2 and Cl2 react, 2 HCl's will be produced. Since the reactants are being used up, we put a minus in front of our x's. Since the products are being produced, we put a plus. To find the equilibrium, we add the I and the C. So this becomes 1.000 times 10 to the negative third minus x for H2. For chlorine, it is 2.00 times 10 to the negative third minus x. And for HCl, it is 2x. We are looking for the equilibrium constant, so we are looking for Kc or KeQ. However, they also told you at equilibrium, the HCl concentration is 1.87 times 10 to the negative third. Since they gave you the equilibrium concentration, we could solve for x at equilibrium. I just rewrote the table that we did in the previous slide, and now I'm going to solve for x because they told you at equilibrium the HCl concentration, which is equal to 2x, is equal to 1.87 times 10 to the negative third molar. So x is equal to 9.35 times 10 to the negative fourth molar. So if I plug this in, so for H2 at equilibrium, it's equal to 1.00 times 10 to the negative third minus x, which is equal to 1.000 times 10 to the negative third minus 9.35, because that's what x is, times 10 to the negative fourth molar. This equals to 6.5 times 10 to the negative fifth molar. And we repeat the procedure for Cl2, which is equal to 2.000 times 10 to the negative third minus x equal to 2.000 times 10 to the negative third minus the x, which is 9.35 times 10 to the negative fourth molar, equals to 1.065 times 10 to the negative third molar. So now we have the equilibrium concentration. We're going to write the KeQ equation. So KeQ is equal to the products over the reactant, which is hydrochloric acid, squared, because the coefficient is 2, and the reactants are H2 times Cl2. I'm going to plug my numbers in. My HCl at equilibrium is 1.87 times 10 to the negative third molar. This is going to be squared. Remember that this x that we solve is the value of x, but hydrochloric acid at equilibrium is 2 times x, so it's going to be double that, divided by the H2, which is 6.5 times 10 to the negative fifth molar, and my Cl, which is 1.65 times 10 to the negative third molar. Plugging in the math, you should get approximately 51. With correct sig figs and KeQ are unitless. Pause the video, try this problem on your own, and then check your answer. At 1280 degrees Celsius, the equilibrium constant for the reaction is 1.1 times 10 to the negative third. If the initial concentration of bromine is 0.063 molar and Br atom is equal to 0.012 molar, calculate the concentration of these species at equilibrium. So 2 clues that this is not at equilibrium. First, they want you to calculate the concentrations at equilibrium, and they provide initial concentration. Therefore, you need to complete an ICE table. So the ICE table is ICE. The Br2 concentration is 0.063 molars, and our product concentration is not 0 because it's given as 0.012 molar. Now we need to do the change. This is a 1-to-2 ratio, so if Br2 decreases by an x, Br must increase by 2x because it's a 1-to-2 ratio. To find the equilibrium, we add the IC, so it's 0.063 minus x, 0.012 plus 2x. Write the equilibrium constant because it is provided for us, and then we could find the equilibrium values of BR2 and BR. So I rewrote the table so it's a lot easier to see. We're going to write the equilibrium constant, KEQ, which is equal to BR in brackets squared divided by BR2. This is going to be equal to BR at equilibrium is 0.012 plus 2x squared over BR2, which is 0.063 minus x at equilibrium. This is equal to the equilibrium constant, which was given as 1.1 times 10 to the negative third. Now we need to rearrange this to solve for x. Cross multiply 0.063 minus x is going to be multiplied by 1.1 times 10 to the negative third. And then this is going to be multiplied by 1. So this is going to be 0.012 plus 2x squared equal to 0.063 minus x times 1.1 times 10 to the negative third. So you need to FOIL the left side, and when you FOIL the left side, you get 4x squared plus 0.048x plus 0.000144. On the opposite side, we need to distribute the 1.1 times 10 to the negative third. That's going to equal to 0.000693 minus 0.0011x. So we move everything to one side. So it's going to be 4x squared. We're going to add 0.0011x to both sides, so then x becomes 0.0491, and then we are going to subtract 0.000693 on both sides, and that will become 0.0000747. This is going to equal to 0. So now I need to plug it into the quadratic equation. Quadratic equation is x equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So if I plug in my coefficients, x is going to equal to negative. The b is 0.0491 plus or minus square root of 0.0491 squared minus 4. A is 4. C is 0.000747. The entire thing divided by 2 times a, which is 4. If you work this out, you should get two answers. One is negative 0.0105 and the other one is negative 0.00178. So in this case, you got two negative answers. So we need to figure out which answer is correct. Since they want the equilibrium concentration, our ice table, and we said that BR2 was equal to 0.062 minus x at equilibrium, and we said BR was equal to 0.012 plus 2x. Since both of the answers came out negative, we need to plug in and check our answers. So it's going to be 0.02 minus 0.0105. This is going to equal, and then 0.062 minus 0.00178, 0.0725, and then 0.06378. For the second one, it's going to be 0.012 plus 2 times negative 0.0105, negative 0.009. So we know that this is the wrong answer and this is the correct choice. So at equilibrium, answer for BR2 is going to be 0.06378 molars, and then so I need to calculate for the other answers, which is 0.012 plus 2 times negative 0.00178. This will equal to a positive 0.00844 molar. So you usually don't get two negatives, but if you get two negatives as an answer, plug it in. The values come out negative, you know the answer is incorrect, and you could eliminate that choice. Pause the video, try this problem on your own, and then check your answer. Here we have the formation of ammonia is 1.45 times 10 to the negative at 500 degrees Celsius. In an equilibrium mixture of three gases at 500 degrees Celsius, the partial pressure of H2 is 0.928 atm and N2 is 0.432 atm. Find the partial pressure of ammonia at equilibrium and find Kc. So in this problem, there's no ice table needed because it's an equilibrium mixture. So I need to write my equation, which is the synthesis of ammonia, so formation of ammonia, which is made from hydrogen gas plus nitrogen gas. It's going to yield NH3, which is ammonia, and now I need to balance, so I need a 2 and a 3 as coefficient. So I'm going to write my Kp, because the information given is in atms. That's going to be the partial pressure of NH3 squared over partial pressure of H2 cubed times partial pressure of N2. Now I'm going to plug in my values. Ammonia, we don't know, we're looking for that. That's going to be PNH3 squared divided by H2. Partial pressure is 0.928 atm cubed. My nitrogen is 0.432 atm. This is going to equal to the Kp constant, which is 1.45 times 10 to the negative fifth. And if you solve for this, you get PNH3 as equal to 0.00224 atm. Since it's partial pressure, we need to put proper unit. If you're struggling with math, isolate partial pressure of ammonia before you solve. Now we need to convert Kp to Kc. So we know that P is equal to Kc parentheses RT delta N. To isolate Kc, I need to divide both sides by RT delta N. When I do that, RT delta N cancels out. So if we rewrite this, this is Kc equal to Kp over RT delta N. Kp was given as 1.45 times 10 to the negative fifth. R is the gas constant, 0.08206 atm liter moles Kelvin. Temperature was given here at 500 degrees Celsius. Needs to be converted into Kelvin, so that's going to be 500 degrees Celsius plus 273. And after I multiply the entire thing, I need to find the change in moles, which is delta N is the moles of the product minus the moles of the reactant. So the number of moles of the product is 2, and the reactants we have 3 plus 1, that's minus 4, so it's going to be a minus 2, my delta N. Now plug in 0.05834. No unit because equilibrium constants do not have units. Sig fix for this one's a little tricky, so you could leave it as is because technically Kp was a constant given. Gas constant is a constant. These are whole numbers always, and the temperature they just gave one digit, so you could leave the answer as is. No units. Pause the video, try this problem on your own, and then check your answer. Here we have 0.05 moles of H2 and 0.05 moles of Br2 are placed together in a 5.0 liter flask and heated to 700. What is the concentration of each substance in the flask at equilibrium if Kc is 64 at 700 kelvins? So first thing we're going to do is we're going to write an equation, and we know we need to use an ice table because you're placing these in a flask and they're going to go to equilibrium. H2 plus Br2, both in gas state, will produce hydrobromic acid, and there's going to be 2 of them to balance it. My ice table, ICE, we need to find the concentration of H2. It's going to be 0.05 moles over 5 liters. Same thing with Br2. It's going to be 0.05 moles over 5.0 liters. And I have no hydrobromic acid. the change is going to be 1 to 1 to 2. So it's going to be x minus x plus 2x for HBr. Equilibrium, I and c added together. So that's going to be 0.01 minus x, 0.01 minus x, and 2x. So we need to solve for x to find the concentrations at equilibrium. KEQ is going to be HBr in brackets squared, because the coefficient is 2, divided by H2 times Br2. Now we're going to plug in the numbers. This is equal to 2x squared divided by 0.01 minus x and 0.01 minus x equals to constant that was given as the constant for KEQ, which was 64. So at this point you can simplify the math by multiplying this out and then moving it to the opposite side and then distributing, or you can make math a little bit simpler by taking the square root. Since the top is squared and the bottom is squared, I could take the square root of both. This simplifies to 2x on top divided by 0.01 minus x on the bottom, because if I really rewrite that, that is the same thing as 0.01 minus x squared. This is going to equal to 8. So now I can cross multiply, so this is going to be 2x is equal to 0.01 minus x times 8. Distribute, so 2x is equal to 0.08 minus 8x. I'm going to put all the x's to one side, so when I do that, that's going to be 10x is equal to 0.08, and so x equals to 0.008. We need to find the equilibrium concentration. H2 is equal to Br2. They were equal to 0.01 minus x. Substituting that in, that's 0.01 minus 0.008 equals 0.002 units of molar. Concentration of HBr was equal to 2x, so that's going to be 2 times 0.008. That's going to equal to 0.016 molar. So those are your equilibrium concentration. When you tackle equilibrium problems, make sure you read the question carefully. If it's at equilibrium, there is no need for ice table. If it says it's going to equilibrium or it's going to reach equilibrium or initial concentration are given, you must write an ice table. And the calculations after that is as before.